All right, can the folks in the back hear okay? All right, so let's get started. So I'm one of the physicists in the MRI facility that works for Peter Bannattini. And today I'll talk a little bit about the basics of MR to give you all kind of just some basic math and physics and concepts of the data that you're measuring, collecting, kind of what's behind it, how it's generated. I decided to not talk about artifacts in this lecture just because I've been finding the couple times I've done this, less is more in terms of what you all get in terms of how much I talk. So we'll try to see how this goes. And I'd like to try to make this conversational. So if at any point there's anything that you have a question about, wondering about, please jump in, ask. I prefer that. I will also ask questions during the course of things just to see if people are keeping awake at this wonderful hour on a Friday afternoon. Okay. So this is kind of the breakdown of the talk. I'll just talk for a few minutes what an MR system is made of, the various pieces, and then we'll get really into what the acronym means and how they kind of come together. And then at the very end, I'll talk a little bit about what makes the images we collect look the way they do, how the properties of the tissue kind of manifest itself in the images that we collect. So, all right, so anybody here who has not been or seen an MR scanner? Okay, so for most of us, this schematic should be fairly familiar. Almost everybody should have seen the magnet. It's kind of hard to miss. So this is where you set up your patients. This is actually where the experiment is done in terms of collecting the data where it's generated. You may also spend a little time in the control room. So you run the scanners from here. Your stimulus may be set up there. The parts that you don't see, and the part really where the magic happens, is all the supporting electronics for the scanner. So behind, usually an equipment room tucked away somewhere that's relatively cold and noisy, there are high-powered amplifiers that we'll talk about what they do later on in the imaging portion, and then there's radio frequency hardware. And this is one of the nice things about MR versus other imaging modalities and it's one of the things that actually got me in the field from early on, is that the quote-unquote radiation that's used is non-ionizing. It tends to be within RF radio frequency, like FM radio / TV frequencies. A lot of this is around us, and it's really not harmful, especially at the energy levels that are used for imaging. And then at the end, after all the data is generated and digitized, there are computers that store, process where the images are actually generated. Okay, so let's get into the acronym. So obviously, at the center of it, we have a really big strong magnet. And I think all of you have had safety, so you know just how powerful this magnet is. Why do we need this? Well, it turns out that certain nuclei have magnetic properties. So i.e., the nucleus of these atoms can act as really tiny little magnets if they're exposed to an external field that's strong enough. So some of these include carbon-13, sodium, phosphorus, xenon. All of these are actually valid nuclei species that have been imaged. But people here know what's the most common one that we do day to day, 99.9% of what we do, unless you do spectroscopy or hyperpolarized imaging? Absolutely right. And why is this important? Why is this useful? Why is this helpful to us? Come on. Yes, tissue water. Actually, tissue water, fat, protein, cartilage, all these tissues have vast amounts of hydrogen atoms in there. And as we'll talk about in the contrast, it's the environments that the hydrogen atoms are in that give the contrast. Okay, but back to basics. Hydrogen atom, if you expose it to a big enough magnetic field, it will actually start aligning itself so that magnets, opposite poles attract. So whatever is the south pole of the magnetic south pole of the hydrogen atom will line up with the north pole of the magnet. and vice versa for the opposite poles. But it turns out that when you put a large pool of hydrogen atoms into the magnet, some of them will align in this lower energy state, but some of them will also, in this lower energy state here, but then a certain portion will align themselves in a state that has a slightly higher energy. And there's a slight difference in these two populations. And this little bit of difference is actually where the MR signal comes from. This little difference between here, between here and here is actually what we depend on for the signal that we acquire an image with. And it turns out that if you make this gap bigger, you can get a bigger difference and hence more protons to image with. Anybody cares to guess how you might make this gap bigger? Sorry? That's actually how you jump between them. But how this gap is made bigger, and they're giving you like more polarization, is actually with stronger magnets. So this is why in the imaging community here, several years ago, we were imaging at 1.5. Now in the NMR center, there are no more 1.5 systems. We're all at 3T. The lowest field system is at 3T, and we have a 7 Tesla human scanner. We have several higher field animal scanners, and it's just because of this phenomenon. You increase the energy gap, but you also increase the difference in the populations between this low and high energy states, and that's what's available for you to image. So again, we have an atom that aligns itself with the magnetic field, but it turns out that not only does it align itself mostly with the magnetic field, but it also kind of turns around it, rotates around it. So this is what we call precession. So there's two types of rotation. There's one on the axis of the atom itself, and then there's one around the field. Okay, and it's this around the field that we're concerned with. So this is actually what leads into resonance. And this is where these two fundamental physics equations.
I apologize in advance for not being able to follow it properly, but in your previous slides, when you said the energy gap, did you mean energy gap of the electron with the neighboring?
No, this is purely an energy state of the nucleus. So just like how electron in the different spin orbitals have different energies, the nucleus has a similar property. So it's the difference between it in a spin in one way and the spin versus the other. Same concept, but a different particle. So this is in the nucleus, not in the orbital bands. In the orbital bands, you're talking about EPR. So that's same underlying physics as MR, but they look at energy in orbital bands. And that's a higher frequency technique, but same.
And over there, that depiction is basically within the.
Yeah, this here, this bar magnet in the middle here floating is actually the alignment of the nucleus, and the little magnet represented by the hydrogen atom's nucleus.
Sorry.
No. Not at all. Okay. So now, going between the two energy states where the hydrogen atom is either aligned or anti-aligned with the magnetic field, so there's an energy gap between those. And it turns out that to transfer between that energy gap, there's a particular frequency at which it's appropriate, it's allowed to jump from one band to the other. So this is one of the fundamental bits of physics. This is what's called Planck's constant here, this h, and this defines the packet of energy, the size of the packet of energy that lets you jump between these two states. Okay, so if your gap is bigger, the constant stays the same, but the amount of energy is different. And then what that means is the frequency of the energy that's related to allow you to make that jump will change. Okay. Why that's important to us is the frequency at which the hydrogen precesses around the main field is related to the main magnetic field by this gamma here. It's called the gyromagnetic ratio. And this gamma here, this is actually a fundamental property of that particular species. So sodium will have a different value. Fluorine, xenon, these will all have different values for gamma. So that in the same magnet, if you're imaging at 3 Tesla, if you want to image these other nuclei, you have to use different frequencies. So this is why on some of our scanners we have what's called multi-nuclear capability. It means the ability to transmit and detect RF at different frequencies because of this property here. So this comes in, this is important because of the concept of resonance. So I have a couple of videos here from Tyler Moore. I checked this morning, this URL is still valid, so it should be available. So when I talked about the atom precessing, essentially rotating about the main field, this is what I meant visually. So you can see the main field is usually in MR, it's along the z-axis. And so in 3D, you have an x, y, z coordinate, 3D coordinate system. And you can see here, if this is the nucleus of the hydrogen atom, it's just rotating around the main field. So it turns out that the frequency at which it's precessing here, okay? If you apply energy to it at a frequency that matches that precession, you can actually toggle it between that low energy state and that high energy state. So this, I think the most common everyday analogy that people use is pushing somebody on a swing. Okay, so you push them the furthest if every time they get back to you, then you give them a little more, you give them a little push. Same way here, if you want to toggle this from its equilibrium state to another state where it's, where it doesn't want to be, but it has a little bit more energy, then it helps if you're pushing at the same rate that it's turning around. So that's shown in this movie here. So you can see here, if we apply a wave at the same rate that this is turning around, you can actually change the orientation of the spin, and hence its relative orientation in the main magnetic field. And the thing to keep in mind here is watch where this is versus where you are on the sine wave. Play that again. So you can see approximately when you hit a peak here, the tip is pointing off, say, along negative y. So do people kind of see this, get this? Okay, so here you have a magnet that's giving you a signal pool, and you're essentially using the concept of resonance to get, to be able to extract a signal from that pool. Now, if you have, put your subject in the magnet and you subject them with, you apply an RF field that's resonant with what's happening in the magnet, what do you think you get back? Okay, so another way of thinking about this. So you have a nice uniform ball of water in the magnet. You give it an RF signal. You don't do anything else. What do you think you detect back? Any different from the one that you transmitted? So basically what happens is, if inside the magnet is relatively uniform, and you apply a uniform RF, you're going to get the same uniform RF back. You may get a little bit less of it because some of it may be deposited in the sample, may not even enter the sample, it may just get transmitted out to open air. But essentially, if you don't do anything in a uniform magnet, if you transmit an RF field, you will detect back the same thing. So you can't tell at that point if it's coming from, something that would represent the patient's torso, their brain, arms, or anything like that. So how we get around that problem is by essentially distorting the field a little bit in a controlled way. Okay. So most of our magnets, schematically, it's a good-sized cylinder, but it's only its rated field, i.e. 3 Tesla, 7 Tesla, 9.4 Tesla, in a fairly well-defined ball around the center of the magnet. Out here, the field kind of falls away pretty rapidly. But in this ball around the center, so this is about 50 to 60 centimeters in our clinical systems, there it's either 3T or 7T to a fairly well-given spec, like parts per million. And this is one thing that we essentially push the vendors for when they're delivering a system to us, that we have as nice a uniform field as possible in this middle region. Okay. So again, if you put a sample in here, there's no way to tell, like if you give it an RF and you detect back the RF, that the sample is re-emitting going back to equilibrium where it's coming from. How you get around that is actually using gradient coils. So this is another set of coils inside the bore of the magnet. And we usually have 3 sets of these. And they're designed to generate fairly uniform gradients in the magnetic field, either along the x-axis, along the y-axis, or along the z-axis. Or in your cases, if you're accustomed thinking in patient coordinates, like uniform fields in right-left, AP, or superior-inferior. Okay. So what happens is when you turn the currents on, so here we're looking in Y, up and down right now, so this will be AP in your patient. When you turn the gradient coil on, you change the magnetic field a little bit between the top and the bottom of the patient. So now what happens now in this case? What happens to the signal on top here versus what you would detect at the bottom here? Perfect, yes. So at the point where your gradient takes away a little bit from the main field, remember of the 2 equations I showed before, the second one, where the frequency is dependent on the main magnetic field, the field here is a little bit lower, whereas up here it's a little bit higher. And in the grand scheme of things, these differences are not huge, they're fractions of a percent, but the electronics are so sensitive and so good, this is plenty for us to image with. So schematically, when the patient is laying in the scanner, and you apply a gradient along the imaging direction of Z, like along the axis of the patient, so superior, inferior, what will happen is the field that this slab of tissue sees is going to be a little bit higher than the slab of tissue up here in the brain. What you can do now is you can actually transmit at a slightly different frequency to detect, to excite or push the protons in this sample here into an excited state. So basically what happens during RF transmission or excitation is you give an RF pulse of a particular frequency. But because of resonance, so the pulse will essentially extend over the entire imaging volume that the coil can transmit to. But because of this gradient and because of resonance, it is only going to excite or push the protons in the slab that matches that frequency into this excited or higher energy state. Okay. So here's a second illustration of that. So Homer here is having his scan, and this is at about this is a 1.5 T scanner. But if we wanted to actually see Homer's brain, what frequency here do we need to transmit at with this gradient in place? Sorry, say again? 64.004. Well, that's if Homer had a normal-sized brain.
Oh, it's a brain.
7, 8, 7.
So in this case, Homer's brain just lies within this single slab of frequency here. So if you want to excite and visualize this here is the only frequency that lets you see that slab of tissue. Okay. So are people appreciating getting what's going on here? Okay. Yes.
Sorry, thanks. Is it true that the spin of the hydrogen protons would differ depending on their environment? So if they're in, let's say, water or bone, or sorry, in tissue cells or in bone or anything like that. So if you're applying the Golden coil from the, so if, like what I'm thinking, or how I'm kind of missing the point, is if as you showed earlier, that it kind of goes with the frequency
Yes.
of the atom, and if you're applying the same frequency across, how do you then distinguish between hydrogen photons and different tissues?
So the question was, I'm just going to say this for the recording. So the question was, how can we tell between the different tissues what happens or how to localize within the tissue? The answer to that is the differences that the hydrogen atoms experience because of the variation in tissue is actually much, much smaller than we impose with these gradients. So it's orders of magnitude difference. So whereas when we image, the main field is at Teslas, we image at milliteslas, so 0.1% of that. But then the difference in environment that a proton may see, whether it's in gray matter or white matter, is probably 3 more orders of magnitude even below that. So it's all relative in terms of the effect of the different fields on the local environment. Is that?
I mean, there is what's called magnetization transfer with pulses. Like sometimes people give really broad frequency pulses to sort of get at maybe the molecules that are like processing at slightly different frequencies. But that's a different sort of, that's a contrast. But there's other things that determine tissue contrast, not this itself. It's the relaxation rate.
Yeah.
It's not the frequencies, but how quickly they relax to either longitudinal or transverse relaxation, which will be covered.
Okay, thanks, Peter. And so this is in one dimension. So typically, we get 2-dimensional images plus slices or 3D images. So this idea of essentially modifying the local frequencies to kind of encode position, you can extend that actually to multiple dimensions. So now we're looking at a patient laying, we're looking at a cross-section of a patient laying in the scanner, and then if we apply a gradient from their right to left, or left to right, depending on how you look at this, again, you have frequencies at this point lower than the frequencies at this point. Now, the difference here is that you've applied a slice select gradient to define which slab of tissue you're going to excite. And then once you excite that slab of tissue, you take away the gradient. So now everything is processing back at resonance. What you then do is you apply another gradient in an orthogonal axis. So our usual mode of imaging is we slice select in Z along the superior inferior direction, but we frequency encode usually left-right to the patient, or in X. So now you've knocked out one dimension with your slice select, and in your second dimension now you apply another gradient a little time later, and again this will give you a variation in frequencies between one side of the patient and the other. And you actually detect all of these things together simultaneously. Okay? And conveniently, there's actually a whole branch of math dealing with this problem. So if you have things with different frequencies kind of transmitting all together, you get something that looks like this. That doesn't really look like any of these completely, but has some properties. I said there's a branch of math called Fourier transforms or Fourier analysis that will let you take any arbitrary time series, 1D or 2D or even 3D object, and it lets you break it down into a series of periodic functions. Conveniently for MR, we use sines, so these are kind of the basic 1D function. But if you have a signal like this that you read out, when you essentially, you do the excitation, say the signal from the arms, so this really low frequency signal and this really high frequency signal, they may have, smaller amplitudes because they're coming from the smaller area. Whereas in the body, these intermediate frequencies may have higher amplitude because they come from, bigger sample area. So what Fourier analysis will do is it actually lets you take this mixture of signals that you detect and actually breaks it down back into these individual components, and it tells you how much of each frequency there was in your original sample. Does that kind of make sense to people? Yes, no? This is probably one of the key points of this lecture in terms of using Fourier analysis to kind of not only encode but then decode the signal that you're detecting. Okay. And then just lastly, this is the last equation I have. But the signal that you detect is essentially a volume average or volume addition of this symbol here, the mxy, means the magnetization in that plane in x and y. And this here is essentially the effect of the encoding gradients. So this S of t here actually represents, this signal here that's a kind of a mixture of all your frequencies. And this bit here is kind of wrapping all those frequencies together and summing them up. As I said, the form of this equation is exactly the form of the mathematical construct called the Fourier transform. And essentially, if you take the inverse transform, or you do the inverse of this equation, you can recover mx0, which is your image, which is your distribution of protons in your slice. Okay. Do you plan to talk more about that? So Andy will talk a little bit more about that on Monday in the advance, but this is kind of the basic idea, concept behind this. Okay. So again, let's go through some fundamental points. So because of how we use the gradients to essentially modify the local field and hence the local frequency at which protons precess, we generate this mixture smorgasbord of frequencies. So we actually acquired what's called the Fourier space, and then we use the transform to give us back an image, essentially a distribution of all these frequencies. This was actually worth a Nobel Prize just over a decade ago to some researchers who did this work in the early to mid-70s. Okay. And this paper is not that old, but it actually has a really neat treatment of Fourier transform in MR. A lot of really cool examples about how to look at the conjugate space and what the effects are in terms of taking away different bits of it and how, what that does to the image. So I would highly encourage to go track this paper down. Okay. Any questions at this point? Okay. So the last bit I will talk about is some basic ideas on tissue contrast and just go into a little bit about bold, since that's what we care about the most. So again, I have a couple of videos from the same site that I showed before. Now, remember we're talking about putting a sample of protons in a magnetic field and then exciting them, perturbing them with an RF field. But then naturally what happens in a system like this is they kind of want to go back to their equilibrium state, right? I mean, we never want to be excited the whole time. Well, at least I'm not that young anymore. But you always need to kind of go back to some kind of rest equilibrium state. And it's the same with these, these microscopic species. So I have a couple more videos here. So the first case here is what's called T2 relaxation. So we have a series of protons at some rest equilibrium state, some population that we can give some energy to, and they'll switch states, and then we can detect them, the signal from them as they try to get back to equilibrium. But the signal never lasts infinitely for an infinite amount of time. It actually decays away with a very characteristic rate. And what happens here, so this is getting back now to your question about what's happening in the different tissues or the different tissue compartments. What will happen is initially when the protons get excited and go into this high energy state or high energy state, they're all kind of marching in step together. But over time, what will happen is because of the little differences in their little microscopic local environments, they will march along at slightly different rates and essentially get out of phase with each other. And the signal that we see kind of depends on these things kind of doing the same thing together and producing a bigger effect. So if they suddenly start doing slightly different things, then the resultant, the addition, gets smaller and smaller over time. So what I want you to pay attention to in this movie is how long this yellow vector is versus how many of these the little red circles with the gray hours are pointing in the same direction. So initially they start off all spinning together, but now as time goes along, they all start doing slightly different things, and then the resultant gets smaller and smaller. Okay.
So that yellow vector is the sum of all the red vectors.
Right. And this particular property is what we call T2 of the tissue. This is its T2 relaxation time. This is essentially a fundamental property. It depends on little bits like whatever proteins may be nearby, whatever electrolytes, metabolites may be nearby. So between gray matter and white matter, this is one type of characteristic of the tissue that determines how the tissues look on the scanner, on the image, in the final images. One variant of this is you can have this same effect, but due to a background gradient in the magnetic field, a small little local background gradient in the magnetic field. And that's called actually T2 star. Okay? And that's actually what's important for bold contrast. I'll show why that is in a little bit. But it's the same idea where you excite the atoms in the tissue. They all start off working together, rotating together. But then because of this background gradient, in addition to the existing differences in tissue property, that they get out of phase. So the star comes in with inherent tissue characteristics plus background gradient. And the last movie I have, and the last bit I'll talk about in terms of tissue properties, is another relaxation characteristic called T1. And actually what this measures is how long it takes to get back for a given tissue, for its population to get back to its equilibrium, i.e. resting state. So diagrammatically, what happens is you had some population that was aligned along Z, the main axis of the magnet. You excite it, you can either knock it partially away from there or completely in this case, so there's no Z component here. And what happens is the population along the Z-axis, you can see here, it should regrow as time evolves. Just the one unfortunate thing about this this particular animation, it shows the T2 decay here as well horizontally. That's independent of T1. But the main idea is to see how this component is regrowing. So that's the important part about T1. So, sorry. Oh, absolutely. So just look at how this bit here is regrowing. This represents the population of protons in their natural state growing back to equilibrium, where there's a characteristic population portion in the low energy versus high energy state. So this is just essentially reestablishing that population. Okay. So, questions? Yep, Daniel.
So why is it that the oxygenation of the blood only affects, is it true that it only affects T2 and not T1? I mean, because I know that's what we meant. Is there a T1 star effect, or is there literally no effect?
Peter, do you want to?
T1 stuff.
Does oxygenation affect T1?
Blood affect T1, or is it just a negligible effect?
It's pretty, well, the oxidation in itself affects T1 a little bit, but it's mostly negligible. There's no, so in that slide I showed last time, there basically it was with Philborn, I mean, he basically showed T2 change, but he tried to measure if it changed T1, but it didn't. So magnetic susceptibility effects don't really affect T1.
Do we know why it would affect T2 and not T1?
Yeah, we know why. We know the mechanism by which it affects T2. It induces magnetic field, microscopic magnetic fields. The spins process at different frequencies.
Yeah, so I have some pictures for that coming up.
Yeah, and so that affects T2 independently of T1. So T1 is purely how quickly
it's not creating like a bulk directional change in magnetic field to affect T1.
No,
Right.
that would be a phase shift, which also doesn't necessarily affect T1 either. But yeah, I mean it's mostly dephasing in the transverse plane, and not growing of magnetization in the longitudinal plane.
Okay.
Yeah. Okay. Any other questions before we? Okay. So I just had some simple examples here showing what you can do with, how you can exploit these different contrast mechanisms to get images that look like a brain. So this is a typical fluid attenuated T1 weighted brain image. This is typically what you would get from either an MP RAGE or a Bravo type of acquisition. So in a T1 weighted image, things with the longer T1 have a slightly brighter signal. And the reason why the fluid is attenuated here is because it is so much longer. The T1, the intrinsic T1 of fluid is so much longer than these other brain tissues that it would overwhelm the signal that you're trying to get at here. So similarly for a T2 weighted image, this is like a spin echo or fast spin echo, here now, again, the CSF has a much longer T2 than gray matter, which then has a longer T2 than white matter. Okay. And then there's a modification of a T2 imaging technique called FLARE where you again attenuate the fluid compartments. So now you get a reduction in the signal from like things that look like or very close to pure water, and then you try to leave behind just the brain tissue that you're interested in. Okay. But this is actually one of the really, really cool things about MR, because of these very subtle differences in the different tissue compartments and the properties that each of them have, you can essentially tailor the timing of all your RF and gradient pulses to really bring out different types of contrast from different tissues. Okay. The reason why we're here is bold contrast. So this cluster of papers, so the first one was Seiji Ogawa's paper where he actually demonstrated the effect of bold in rats. And then this cluster of papers from, almost 25 years ago now, all kind of simultaneously converged on demonstrating the bold effect in human subjects. So where that comes about is what Daniel was asking about earlier. Turns out that deoxygenated blood, i.e. where there's a little bit of hemoglobin where oxygen is not bound, is what we call paramagnetic. So it means it has a propensity to increase the local magnetic field around it. So that's why in the blood vessel here, these lines are closer together. So when the magnetic field lines are closer together, it means that there's a higher field. Why this is important is because, if you have a region of brain which is not active or not so active, there's some deoxyhemoglobin in the vasculature around their capillary bed, venules, and it turns out that there's enough of a gradient here. So the difference between the magnetic field inside the blood vessel versus in the tissue, so there's a magnetic field from high to low, and the gradient around the vessel causes the protons in this area here to decay away faster because of this background gradient. So this is this T2 star effect that I was hinting at earlier. So again, it will be protons that essentially lose coherence with each other. That's T2. But because now there's an additional background gradient in the magnetic field, they're losing coherence even faster. Okay. Why this is important for us as imagers, it means by the time we get to image this, there would be less signal than there potentially could be if this field were more uniform. Okay. Are people appreciating that? Yes?
Sorry, I'm not sure I exactly understand what you mean by like background stuff going on.
So you can see the spacing of the magnetic field lines in the blood vessel. Here, they're fairly dense, and they're denser than they are out here. So the lines here are further apart. So it means schematically, diagrammatically, it means that the magnetic field in the blood vessel is higher than it is out here in the peripheral tissue. And that difference in the field from here to here is actually what we term a background gradient in the tissue. So what will happen is on a microscopic scale, when you excite an image, because this is a slightly higher field, the protons precessing here will precess at a slightly higher frequency than the protons precessing out here further away in the tissue. So it means they lose coherence faster. So think of this as a single voxel, because this is a few microns. Okay, so this is tiny. But if you have things within your voxel that are losing coherence so quickly, the net signal that you have coming out is smaller. So remember from the T2 precession diagram, as things lost coherence with each other, the net vector that we could see and measure became smaller.
Just in relation to that, because you were saying this background gradient obviously is what creates the T2 star image, but the background gradient also, this exists when you're taking a T1 or T2 image, so how is it that you're specifically targeting this in T2 star to get a different image?
So we focus on the different types of tissue contrast because of how we time the different pulses in our MR sequences. So this is why you have a particular sequence for your structural scans. So those, we make them T1 sensitive. For our functional scans, we take measures to make them T2 star sensitive. So this is why I was saying it's so cool that what we can do with just, it's the pulses themselves from sequence to sequence, they are different, but they're not so different. But the big difference between the different sequences is the timing of the different pulses.
So for T2 star, does that mean that they're faster? So that they're going more quickly?
So for T2 star, this is what we term as a gradient echo type of scan with a long echo. So it means that the type of readout that we don't do any kind of refocusing except maybe with gradients. So these are the imaging gradients that I talked about a little bit earlier in terms of how you localize and you also use for reading out. So by using those gradients appropriately, we weight the imaging sequence and the data that you collect towards T2 star. Yeah. Andy. Yeah.
So this is a pretty subtle effect. Compared to imaging gradients, this effect is very small. Okay, so the rate at which the spins are getting out of phase with one another within the voxel is quite slow with this. It takes a while for them to get completely out of phase. So typically the TE, the time when we acquire the data, in this will be like 30 milliseconds.
At
To give
3T.
Time, yeah, at 3T. To allow the spins time to kind of all get mixed up and jumbled up with respect to each other. And then the more vessels like this there are, the more you'll see the signal attenuation because there'll be more, in those voxels, there'll be more out of phase with one another. For the structural scans, the TE is way shorter than that. It's like the order of 3 or 4 milliseconds. And in that time, they don't have so much time to get out of phase with one another. So they'll be more or less lined up and the signal will be adding coherently, then you get a strong signal there.
And you won't have this background weighting, this T2 star weighting. Now, as Peter hinted in his first talk, kind of the fortuitous thing that made this work is when a brain region becomes active, there's actually an oversupply of oxygen, nutrients. So what tends to happen is the blood oxygenation actually increases in areas where the brain is active. And what happens in those cases is now the field within the blood vessels look more like the background or the surrounding tissue. So if there's less difference here and less of a gradient, then what happens if you measured the signal now with the same timing parameters that you were in this case? Sorry?
I'm not sure, but I think the T2 and T1 would be similar.
So, sorry, if
In the vessel and in the background, the T2 and T1 would be similar as compared to the earlier case.
T1 not so different, but the T2, T2 star, that's the effect that we're actually measuring here. No, so what will happen is in this case where we had high field inside the vessel, lower field outside, and then this gradient in between, you have a lot of dephasing happening here, so we have a lower signal in the time of the imaging experiment. Here, because the environments are more similar, there's less dephasing. So if you use the same timing parameters to measure these two conditions, you should actually get more signal in this case than this case. And that's just because, again, the difference is smaller here between the inside of the blood vessel and the outside than it is here. Okay. And if you look at the time series of a bold experiment, this is typically what you see. If you have a stimulus causing a particular brain region to work in these areas here, where the red line is high, you can see that the black line, which is actually the measured signal from images collected in that brain region, also go up. So it's because of this effect where the oxygenation changes causing the blood vessels, the tissue, the fluid in the blood vessels to be more matched to the background. Right? So you have less dephasing and a higher signal. Okay. Is that okay?
I have a random question.
Absolutely.
If you go back to the image with, go back 2 slides, that slide. So if the magnetic field is technically higher inside of the veins, if you were only interested in veins, let's say,
Yes.
if you had a very short TE and you did that image, you get a very good image of the veins. Like a better image of the veins compared to.
Well, the thing is, the reason why this contrast works is you have to give it time for these differences, because remember the video is if you image too early, they're still relatively in phase together. It's only after you wait some time that the differences pop out.
So just to try to explain, I mean, let's say this whole thing's surrounded by a big voxel, and this is a big voxel, and all your spins are in it, Right, I mean, so if you have a very, very short TE, it doesn't give them any time to process, so therefore they don't really destructively add.
Mhm.
And so that signal, the veins will be high, the tissue will be high. So, but with when T gets longer, the vein signal will be low and the tissue will be less low. So then that's why the veins look like these dark dots in a long TE star image.
But we do make pictures like that.
Yeah.
Not with long TEs to make.
Right,
Yeah.
to highlight, so actually, that's the whole basis of, so when I talked about last week, susceptibility weighted imaging, that's sort of pioneered or coined by Mark Hickey, in which he actually does exactly that. He collects long equitime or like T2 star weighted scans, and it basically highlights any magnetic field inhomogeneity, so it gets at signal dropout, but it also gets at veins, and the veins show up as dark dots.
Okay. So, and again, this effect of looking at what happened to that change in oxygenation, this is how we derive our parameter maps after we, collect these time series and do our statistics on these types of images. Okay. And then, this is good timing. So for the rest of the course, we'll have a lot of people talking about other different types of tissue contrast. So this is nowhere near an early paper on diffusion, but it was written. It was written by one of the pioneers in diffusion imaging. Peter just mentioned Mark Hickey. Jeff Dunn also had really nice paper from a few years ago, just some gorgeous, gorgeous images showing what you can do with phase imaging at 7 Tesla. They're actually even now trying to collaborate with some of the clinical groups to see how these imaging techniques and how they look at the tissue properties, if there's some clinical value to that. There are also different techniques for imaging, like how much water, how much perfusion is happening to different brain tissues. Again, Peter mentioned earlier, magnetization transfer in terms of looking at the protons in these large pools of proteins that may not resonate exactly at the water frequency, but they're a little bit off. And there are all these different techniques that you can use to explore all these different pools of protons with slightly different properties. And what's actually really cool about the NIH is that a lot of these folks either are still here or were here. So Jeff will talk later on in the series. Alan Koretsky was also a pioneer in the field of perfusion imaging, and Bob Balaban is actually the scientific director of Heart, Lung, and Blood. So there's a lot of history and a lot of expertise around, and definitely urge you to take advantage of that. So that's it. I will take any more questions that you have, and thank you for coming and persisting on a Friday evening, persevering. Daniel.
So when you're measuring, so when you have the amplitude of your signal, is that the value, is that the amplitude of the frequency at one point in time in the T, or is that the rate of decrease of the T2 over the course of the T? Does that make sense what I'm trying to say?
Let me see if I can try to get, so you're asking about the signal that we measure at a given voxel?
Yes.
So in a given voxel, because essentially that represents a particular frequency, the amplitude of a particular frequency that we detected back from the subject.
Yes. So.
Well, if I could add.
Sure.
I mean, the signal from a voxel is really complicated. I mean, it's a combination of the relative proton density.
Right.
It's a combination of how much tissue you have in each voxel that might have a different T1 or T2 relaxation rate.
Yeah.
And then a function of what your equitime is or what your TR is that determines how much you're weighting the T1 or T2.
Okay.
So it's a whole bunch of those, it's all those things combined.
Yeah. Okay.
So, and you can tease them out if you modulate enough of the parameters.
Right.
But typically with MRI, you have to choose all the parameters, and then it's a combination of those.
Right.
So
Okay.
I don't know if that.
Yeah, no, I mean, it's more complicated than like I'm thinking it is right now. But I think about it so much.
And the whole point of saying, so like it's common jargon in MRI is T1 weighted or T2 weighted. And that's just simply to maximize the difference in those two exponentials. There's an exponential curve for T2, exponential T1, and it's just to sort of get the sweet spot that you can get the most contrast.
So you're saying the measurement of the amplitude at that sweet spot?
Exactly.
Okay. I think, yeah, that's what I was trying to say. Is it the measurement at a sweet spot, or is it the measurement of the whole curve? Like the rate of the whole
It's
curve?
just at the sweet spot.
Okay.
It's
Or-
just
or
at whatever
whatever
timing
spot.
parameters you choose in the sequence. But you try to choose your parameters to enhance the contrast
Right.
that you're looking for in that particular experiment.
So you can choose a super short TE that is more proton density, because then all the spins have the same signal. And
Okay.
it's just based on the proton density, how many are there,
Okay. That
so
makes sense.
things like that.
And I mean, later on, we'll talk about multi-echo experiments where you
You
make
can.
one image at one TE and then another image at late
Right.
TE and another one, and then you can track the whole curve.
Okay.
And then you can trace the whole curve down. And
Okay.
then you can get a handle on T1 or T2 down to you.
Okay.
You have a question, Jerry?
So for the bold signal, it takes longer to acquire. Will that signal dropout change in terms of space? What I'm saying is like, will you be acquiring bold signal from a voxel where maybe neural activity wasn't quite observed by the time you acquire the signal?
The thing is, with bold experiments, you're actually looking at how the signal behaves over time. So if your subject is relatively stable in the scanner, even though, so a particular voxel may have low signal, but over the course of the experiment, it should always have low signal. It should only fluctuate in areas where, it should only go up and down in areas closer to where there is activity, where you're looking for activity.
You have to measure like what direction the blood is flowing in, and then trace back a couple 100 milliseconds to get to where the actual signal's coming from.
So this is another fun area of debate.
Yeah, I mean, so neural activity, in my previous talks, I mean, so like neural activity first happens, and then a couple seconds later, the blood flow starts going, or the blood oxygenation starts going on, and then after about like 10 seconds, it's plateaued. And then when neural activity stops, it takes another 10 seconds for it to go down to baseline. And that's sort of the limit we have to live with. And we can maybe deconvolve that and go back, but the problem is that latency varies all over space depending on the vasculature. So it's hard to sort of go back. And you just have to infer within a couple seconds that's where the neural activity took place. And so you can give a very brief stimulus. So if you give even like a 5 millisecond stimulus, you can see a response 5 seconds later and then it dies down. So that's all due to the blood flow response, the hemodynamic oxygenation response. So I don't know if that was your question. Okay.
Yeah, thank you.
The individual images are taken in about like 50 to 100 milliseconds. So that when you're doing a bold experiment, the individual images are taking about 50 milliseconds to maybe acquire each one. So you're really kind of getting a snapshot of that moment, right? But the bold responses, like Peter was saying, they take seconds to develop and go away. So it's not like you can't really measure the bold response in what's happening within those 50 milliseconds, right? Because it's all blurred out by the blood flow.
But it's just the difference between the before and
Yeah,
after.
yeah, and it's relative to itself. The voxel is measured relative to itself, I guess.
Marin?
Yeah, I have a question about what is like really simple, but we have a gradient of magnetic field in the 3 dimensions that are always there.
No.
No.
The gradients are turned on at specific timings depending on what you want to do for your given experiment.
Okay. So for one run on, it could be there. Like it would be fixed at the beginning of the acquisition of a run. Or is it?
No. I mean, an experiment involves turning these things on and off
Okay.
in a given pattern over time.
Okay.
So that's why you hear the periodic noises
Okay.
in your experiments. So
So that's the adjustment of the gradient.
the noises are essentially the gradients turning on and off.
Okay. And then, so you adjust and then you send a radio frequencies that match the gradient of the particular outside your frame.
Well, so like I was trying to get at is you can play these things in infinite number of orders and patterns. And it's really to bring out the different types of tissue and the contrast inherent in the tissue. So there's no fixed. I mean, there are certain patterns of pulses that will enhance certain types of contrast. So for example, if you play a radio frequency pulse and you read out very quickly, as Peter was saying earlier, that's very proton density weighted. If you wait a little bit longer, then you can be T2 or T2 star weighted, depending on if you have another pulse in between there. If you wait a long time before you excite again, then you can essentially impart T1 weighting. So remember T1 was how long it took to get back to its equilibrium state. But if you essentially excite again before it has a chance to fully recover, then you can tell how quickly it is recovering. So things with shorter repetition times, i.e. shorter intervals between exciting the same bit of tissue over and over again, those tend to be T1 weighted. So that's kind of a general, some general, mechanisms to bring out tissue contrast, but there are so many now to. Savannah.
Yeah, Nicole. But
Yeah,
anyway,
sorry.
So the way I've seen this before is that like the data comes out of the scanner in K-space, and then the Fourier transform turns the information in K-space into image space, basically.
Yes.
You talked about the Fourier transform, parceling out the different frequencies in that combined frequency that we first get. So again, K-space in my mind, I get these images of like just these random white dots that are like condensed in the middle and spaced out later on. So
Absolutely.
Can you sort of explain what that image means and what, like, in relation to these frequencies, like, what is that actual image of K-space representing?
I wish I almost included that a picture of that, but so I think maybe the easiest way is to go back to the 1D case. Yep. So in this case here, this will be your measure of, this would translate to your image intensity. And this is telling you how much energy there is at this frequency. Okay.
So
Thanks.
if I could start just really quickly.
Sure.
A very quick. So just a really quick idea of K-space. If you're describing it sort of qualitatively, the big blob in the center and all this stuff going out. So the big center part is where you have no encoding gradients, and that has the most energy. So that's the overall. That's sort of related to the overall low frequency signal. So that's the lowest
Right, and
frequency.
the outer parts are like the contrast between tissues.
Well, the outer parts, so it's directly related to the spatial frequency.
The edges.
The edges. So if you cut off the outer parts of K-space, the image will get blurry.
Right, yeah.
If you cut out the middle, it will just show the edges.
So actually that AGNR paper I talked about actually has some really nice examples of that.
Yeah, so then I'm just wondering how that translates into like these individual frequencies.
Okay, so if you look at K-space on the same 2D grid like you would the image, in the middle point, there's no variation at all. That's your DC. That's kind of your image average. If you go 1 point off along the x direction, then you have 1 cycle of variation along x. If you go 1 point off in the y direction, then you're 1 cycle of variation in y. And if you go along the diagonals, there's kind of a hybrid function that does both 1 cycle of variation in x and in y. So the Hutel and Song book, functional MR book, actually has one picture that has a really nice depiction of this, where they show K-space and they have different points along K-space and they show the variations that these things account for. But this gets back to Fourier theory, where all these variations, if you add them up, you can recreate, if you have enough of these regular functions, you can add them up and recreate almost any arbitrary 1D or 2D or even 3D waveform or object. Yep, Leanne?
Will temperature affect the T1 or T2?
Yes, there is some effect. They're very subtle, so you have to do particular things to kind of enhance that. But yeah, people do temperature imaging with MR.
Which one influences the temperature?
I don't have much experience. I would probably guess T2, but I can't.
Yeah, it's really a subtle effect. There's actually a PNAS paper with Yablonsky that looks at brain activation, claiming that he sees a very, very small temperature shift, and it's MR phase, which is sort of T2, kind of like T2. But it actually, temperature mostly affects diffusion of the spins, which you can actually probably measure with looking at diffusion coefficient a little bit, maybe. So.
But the subject will get heated during overscan.
No, the RF isn't enough to heat the subject. So when I mean it changes the temperature, it means like induce heat things that change the temperature. So the RF does not, it's not like a microwave. It's only RF. It doesn't really heat the subject. I mean, a little bit, sometimes you might get a little bit of heating, but it's actually not that, it's not that much.
Any more? All right, thank you all.